Today's lecture concerns one of the conversion factors that allow us to change money from one form of payment to another. And in particular, we're looking at the arithmetic gradient conversion factor. You'll recognize this diagram. We've seen it a few times before. That shows the conversion factors that relate the four different forms of payment that we look at. The present worth, which is money today. Future worth, money at some point in the future. Annuity, which is an equally spaced series of payments that are equal in size. And down at the bottom here, the gradient, which is an equally spaced sequence of payments where the payments themselves actually increase in size each period. And we're looking at this relationship here between the gradient and the annuity. You notice we only have one conversion factor. Between the other forms of payment we have two. Because just by and large, people tend to go from a gradient to an annuity and very rarely the other way. So we just focus on that one direction conversion. So with the arithmetic gradient conversion factor, we're going from a gradient, G, to an annuity, A, at some interest rate, I, and involving some number of periods, capital N. I want to remind you, before we get into the details of that, how a gradient works. In fact, a gradient has kind of a complicated structure to it, which is important in the conversion factor. The gradient has two parts to it. The first part is what's called a base annuity, which has the form of an annuity, being an equally spaced sequence of payments of an equal amount over time. And for example, here's an annuity for n is equal to 7. Now, the base annuity for a gradient is called A prime. In addition to that base annuity, the gradient has a gradient part, which is an increasing sequence in the amount G. I'm not going to complete this with the detailed arrows. But the point is that this increases linearly by the same amount each period. So that the increase, there's zero increase at the end of the first period, just the A prime. At the end of the second period, there's A prime plus G. At the end of the third period, there's A prime plus 2G. In the fourth period, A prime plus 3G. And so forth. So that at the end of the nth period, it's A prime plus n minus 1 G. Yeah? So it's kind of a complicated structure, but it kind of makes sense because if we're going between a gradient and an annuity, well, the gradient already has an annuity in it, and that's that base annuity, because the gradient does start at the end of the first period in that sense. So we don't need to convert that A prime part. All we need to convert is that G part. Now, that conversion process is a little bit complicated, and you can check your book for the details of it. But in general, what we do is we take those individual small, the little G's I had in my diagram, these G's here, and we take them to a future worth individually, and then to get total future worth to an annuity using the sinking fund factor. And it's kind of a complicated process. I won't go through it here. But we go through that process for the G part, not the base annuity, the A prime part. And for then that G part, the formula we end up with is A is equal to G, and that G is just simply the increment on a year-by-year basis, times 1 over I, so 1 there, minus n over 1 plus I to the n minus 1. But that doesn't yet include the base annuity. And the conversion factor then associated with that is A slash G I percent n, and that's going to be 1 over I minus n over 1 plus I to the n minus 1. But when you actually convert from a gradient to annuity, you have to take that a prime part into account. So if you like, this formula is insufficient. It's a little bit complicated, but you just have to remember this. That really what you have to remember is that the whole formula is that a, this is, if you like, a different a here because it takes into account the base annuity, is going to be that a prime, that base annuity, plus then the conversion from the gradient. So this is kind of confusing, and there's no other way to get around it other than explaining it and remembering it, is that we're using the g and the a in two different ways here. Sometimes we use the g just meaning that gradient amount, that little increment from year to year. That really starts at the end of the second year. And other times we use the gradient to mean both that increment and the base annuity. Similarly with the a, sometimes we use the a to mean the annuity that you convert just that incremental gradient amount to. And other times we use the a to mean both that base annuity plus that incremental gradient amount. So it's confusing. All I can do is apologize for it, just the way it is. If you remember it, it's OK. Separate out that base annuity, use your conversion factor on the gradient part, and then the total annuity that then can be calculated is composed of both the base and the gradient. So let's look at an example. Here we have a lottery. It pays $1,000 at the end of the first year, $2,000 at the end of the second, etc. for 20 years. If there's only one prize in the lottery and 10,000 tickets are sold, and you can invest your money elsewhere at 15% interest, how much should you pay for a ticket? That's kind of a complicated question because the information you need is a little bit masked. First of all, we do have a gradient here. And this gradient has a base annuity of $1,000. And the gradient itself is equal to 1,000. Right? Because the lottery pays $1,000 at the end of the first year, $2,000 the second, and so forth. So that $1,000 is in the form of annuity. It's paying the $1,000 every year. But starting at the end of the second year, there's another $1,000 increment. And then it goes on from there. So you have to sort of take the information and break it down into two parts, the base annuity and the gradient. The interest is also a little bit expressed in a different way you've seen before. You can invest your money elsewhere at 15%. It's simply another way of bringing out the fact that the money that's involved in this lottery can be moved through time at this 15% interest. We'll see later that the interest you use for converting money from one form of payment to another, the choice of a value for that is actually a fairly complicated thing. And in word problems, if you see an interest rate expressed, that's usually the one to use. But there's many different ways that that interest can be derived. And this is just another way, how you can invest your money elsewhere. But it's the 15% interest that's needed. And then the n. What's the n here? Because we talked about the difference between the base annuity and the gradient. We can see that the n for the base annuity is clearly 20. But what about the gradient? Is that 19 or 20? Well, the answer is that it's also 20. Because that gradient is defined to start at the end of the second year, that increase beyond the base annuity. So even though it starts the second year, it's still a 20-year total period, a set of periods that's involved, not 19. So n is definitely 20. Now, finally, how much did you pay for your tickets? A complicated question, too. Does that mean that we want a present worth or what? Because there's 10,000 tickets sold. And yeah, the idea here is you do want to calculate a present worth here, not an annuity or anything else. If you calculate the present worth of the prize, you can divide that by 10,000, and that will give you the worth of one ticket. That's the logic here. So we want the present worth. We don't have a formula for calculating the present worth directly. However, we do have one for calculating an annuity from the gradient values given. So let's calculate an annuity first. The annuity is going to be the base annuity of 1,000 plus the gradient amount of 1,000 times the arithmetic gradient conversion factor, which is 1 over I of 0.15, minus n, which is 20, over 1 plus 0.15 raised to the nth power, which is 20, minus 1. And that works out to be $6,365.10. That is an equivalent annuity to this gradient prize value. We want to convert that to present worth using our uniform series present worth factor, which would be the 63, 65, 10 times P slash A 15, 20, which we can calculate explicitly or from a book. Its value, in fact, is 6.2593. And then our total value of the prize as a present worth is $39,841.07. And since we have $10,000, 10,000 tickets to be sold, we divide that by the 10,000. $3.98. Now, this is kind of an interesting problem because you often see lottery prizes of this type where instead of, they'll say it's a $1 million prize, but then they'll say it's paid at, say, $100,000 a year for 10 years or $50,000 a year for 20 years and so forth. And really they're misleading you by saying it's worth $1 million because the present worth, the worth today of such a prize, is considerably less depending on what interest rate you use. And in fact, you can calculate that present worth and you can calculate the value of an individual lottery ticket using a process very similar to this one. So that's the arithmetic gradient conversion factor. We only look at the one rather than reciprocal because it's what most commonly used and provides us the opportunity to convert from a gradient amount to an annuity, and from there we can convert to any other form of payment we wish. Thank you.